In this video, I would like to introduce the concept of elastic potential energy uh, and how we can calculate this energy in spring-like situations. As you may recall in my earlier video, we talked about, or at least introduced the idea of elastic or spring potential energy as a stored energy um, that is stored in things like springs. When a spring is compressed, such as this picture over here, a certain distance of, say, x, then we have some energy that will be stored within the spring. The deformation of this spring results in elastic potential energy being stored in the spring because there's work that is done by external forces, such as this block applying a force on the spring. And hence there's energy stored into the system as internal energy, and specifically that's called elastic potential energy. So then the question becomes, how do we calculate this spring potential energy or elastic potential energy that's now gained into this spring system? Well, it turns out after a bit of modeling in class, we might see or come to the conclusion that when we looked at the force versus displacement graph, and which was Hooke's law, if you recall, the energy that's stored in the spring is really equal to this area that is under this curve. The area under that curve represents this elastic potential energy or the work that is done on the spring. So remember on our Hooke's Law lab, we plotted force versus the stretch, and you got this nice linear relationship where the force, the spring force, was directly proportional to the stretch distance. The more you stretched it, or the more you compressed it, the more force you had to apply for the more stretch that you had. The slope of this graph, okay, the slope of that graph represents K, which we called the spring constant measured in newtons per meter. And then we came up with this equation that the spring force is equal to the spring constant multiplied by x. And we put absolute value signs. Why? Because technically there's a negative sign in there. So as I mentioned earlier, the area under this force versus displacement graph represents the energy that is stored in the spring system. To calculate the area, we have to find the area of that triangle. That shaded area that is just shown here, let's just calculate over here. Maybe we'll write it on the side here. Area would be the area of a triangle, which is 1/2 times the height multiplied by the base. And you can see if I stretched it a distance x, the base would be x, and the height, well, the height, if you recall, at that position of x, you call right here, that force would be the spring force. And the spring force is equivalent to k times x. So it's really 1/2 times kx multiplied by x, which is really just equal to 1/2 kx squared. That represents the area, and we mentioned earlier that the area represents either the spring potential energy or the work that is done. So this is really equal to the spring potential energy. But you might be asking, maybe this might come up in a problem, but what about problems where, let's say, you have a spring that is, say, partially stretched? Let's say this is the spring that is unstretched, so this position here, x is equal to 0, and now here's a situation the spring is stretched to a distance, an extra little distance, x, in here. And then you decided to stretch it even more. And so now it stretches to this distance x. So maybe we'll call this xi for the initial position and x sub f for the final position. So, well, how much energy would be stored from going from this location to this location in the spring? How would we calculate that spring potential energy? Well, if you think of it graphically, and there we have like Hooke's law, where this position right here is the x initial, and then this position right here is x final. So how do we find the energy that's stored from going from this position to this position? Well, it's the same concept. You have to use the area under the curve, but now we're looking at the area under the curve that is bound between the initial position and the final position here. We're looking for this area that is bound between these two locations. So the area under the curve would be like taking the area that's bound between here. Suppose you could use a trapezoid formula, but I would just say take the area of the large triangle, which would be this area, 1/2 kx final squared, minus the area of the small little triangle right in here, which would be minus 1/2 kx initial squared. And then that would result by subtracting the large triangle and the small triangle and getting the area that's bound between these two locations, which is the area of that trapezoid. I guess you could simplify this if you'd like, take out a common factor of 1/2 k, and you would just get x final squared minus x initial squared in the brackets, which then results to this formula right in here. The general formula they're going to give you on the AP formula sheet is this one right here. All right, then you now can proceed on to the next example.